Relatively Prime was made possible rather unexpectedly by the 159 people who tossed me some scratch on the Kickstarter. I'd like to thank in particular Aaron Gulliford, Scott McDonald, and Martin Veneroso, as well as my Kickstarter producers, Daniel Greenspun, Douglas Dollar Stewart, Jay Frosting, Colin Wright, Cody Palmer, Martin Dominic, and Edmund Harris. Thank you all so much. And also, thank you everyone whose name I didn't say. You are all equal in my eyes, even if you did give me different amounts of money. So thank you for making this show actually happen.
Well, I remember I thought, because of the interest in the original post suggesting the idea, I thought that as soon as I posted the problem, that people would just immediately start commenting. It was all felt. And it didn't happen instantly. I had to wait several hours before there were any comments at all. But it did pick up pretty quickly after that, and I can't remember. Definitely within 24 hours, it was clear that a conversation was starting. And some sort of strange transition took place, but I wasn't really expecting to solve the problem when we started, because it was quite a well-known, seemingly pretty hard problem. And just gradually things happened. One of the main things that happened was changing from the original approach to a slightly different approach.
So about how far in did that start to happen? Was it clear that the change of approach would be useful?
Probably 3 to 4 weeks in, I think. By that stage, we'd raised a lot of interesting questions and had a lot of interesting discussions about the first idea. So I think we'd sort of built once the approach that was destined to work was started, things went very quickly. The obstacles that occurred would be sort of sorted out within a matter of a day or two, and things like that. But, whereas with the first approach, we had interesting thoughts about interesting questions, some of which we could answer and so on, but it still didn't feel as though we were... It always felt as though we were an idea or two short of being on course to prove it. But I think it'd be interesting to look back and see how much of what we discussed during the first phase was actually used in the... I think some of it was actually, I was thinking back, some of it definitely was. There was a particular technical problem that made things difficult but not impossible. And then we came up with a neater way of dealing with this technical problem, which streamlines what we did later on quite a lot. So I think for the first few weeks, first three to 4 weeks, whatever it was, it felt as though we were going to end up at least with a very much more thorough understanding of the problem and quite a lot of interesting sub-questions and so on, and this nice wiki with and then suddenly, quite surprised, suddenly we realised actually we're going to solve this thing. It's good. It's not looking so bad after all. But subsequently there have been other projects that have not ended up solving the problem that they started with, but that have been, they still seem to be valuable in the sense that this phenomenon that we observed with the first one of getting very quickly to a much deeper understanding of the problem than we started with still happens. It's then a kind of question of luck whether you can push on from that to finally solving the whole thing. But you can get to a level of understanding of the problem that in a short time that would take an individual a very much longer time. even if you don't solve the problem. So I feel as though this whole process is an interesting one, regardless of whether it actually solves problems. It does something much faster than can be done by one or two people on their own.
I am Samuel Hansen, and you are listening to Relatively Prime, stories from the mathematical domain. That was Professor Timothy Gowers of Cambridge University talking about his polymath project, where he and many others from around the world collaborated through the comments on his blog to find a new combinatorial proof of the density-Hales-Jewett theorem. He was not sure that this approach would yield results, but unexpectedly, it did. And it's that idea of the unexpected that this episode is all about. We'll talk about how a sociologist's observation about the statistics of networks decades later might help predict epidemics. How an epiphany had while giving an exam led to the questioning of the usefulness of the most well-known of all the mathematical constants. But first, let's have a story about how the Cambridge Sandwich Year and a unicycle society can lead to traveling around the world talking about the mathematics behind throwing things in the air. And to tell that story, here is Colin Wright.
The story behind it, and this of course, as with stories that are told over many years, indeed decades, the story may very well have mutated. But the following story is close enough to the truth, in that I started to juggle when I was at university. Well, actually, I don't remember learning to juggle. I learned to juggle when I was, I don't know, 12, 13, something like that. But I'd never taken it beyond the stage that a lot of people take it to, which is to just be able to juggle 3 balls and perhaps 3 apples and on a really good day 3 bananas. So I never really did anything with it. But I took it up fairly seriously when I was doing my prelim year for my PhD. When you study at Cambridge for a PhD, you have to do an sandwich year that's between the bachelor's degree and the PhD. It's called Part 3. Long story. So I was in that year, and one of the guys in my college, it turns out, builds bicycles as a hobby. So people would come to him and say, "I want a bicycle that has the following characteristics," and so he would piece together a bike. He'd get a frame from here and brakes from there and wheels from somewhere else and so on. And I used to do a lot of bicycle touring when back home in Australia. So we got to chat. And he said, "I've built a unicycle." Now, a lot of people think I'm very clever, but this is a great demonstration of how stupid I can be, because I said, "Oh, I've always wanted to try and ride one of those." So he actually brought the unicycle to college after Christmas. And so then, of course, I was honor bound to try and ride it. And so I learned to ride the unicycle. And I went along to the Unicycle Society, the Queen's College Unicycle Society. And most of the people who were there could also juggle. And so I thought, well, I can juggle. So I made 3 beanbags. And I went along to the university's Jugglers Association and said, "I can juggle 3, but I'd like to learn how to juggle 5. And after a while, they stopped laughing at me and said, "Well, can you do 3? I said, "Yes, I can do 3. They said, "Can you do 4? And I said, "Well, I've only got 3. So they gave me an extra one and said, "Now, can you do 4? And I said, "No." And so they showed me how to do 4. And I went away and I came back the following week and I could do 4. They were very surprised at this. Going from 3 to 4 in less than a week is quite unusual. But I've always been fairly talented at totally useless things in life. And I could do 4. So they said, "Here's how you do 5. And they showed me how to do 5. And so I started to work on that. And working on 5 is horrendously tedious. I mean, seriously, seriously tedious. And after about 20 minutes, I stopped and I looked around the room, and nobody else was juggling 5. Everybody else was doing different shapes, patterns, structures, and tricks with just 3. And I thought, that's much more interesting. And so, abandoning trying to do 5, I went around to people and said, show me a trick. Show me something interesting to do with 3. And people showed me things like 1 over the top, and 1 high, and 1 high pirouette, and behind the back and under the leg, and so on. And I wrote all of these down. And then I went up to a guy called Mike Day, and I said to Mike, show me a 3-ball trick. And he showed me the most amazing 3-ball trick. Anybody who juggles 3 balls semi-seriously will know of this trick called Mills Mess. And I was stumped. I could not write down a description of Mills Mess. It was amazing. And now that I know it really well, it's not actually that complicated. But back then it was completely mind-blowingly complex. And there was no way to write it down. And we thought there must be ways of writing down juggling tricks. I mean, we have ways of writing down language. We have ways of writing down music. We have ways of writing down dance, actually multiple ways of writing down dance. So there must be a way of writing down juggling tricks. And we looked through all the back issues of the juggling magazines that we had. There are magazines published about juggling. And we looked through the back issues, and none of them had descriptions of juggling tricks. So we decided to invent a notation for juggling. Now, this didn't happen overnight. This took some considerable time, and our early attempts were very poor. They were inadequate to describe many of the tricks that we thought a notation should be able to describe. And eventually we hit upon a scheme that seemed to work. And so we used it to write down loads of different juggling tricks that we knew. And then we discovered that if we arranged those tricks in just the right way, they fell into a pattern. There was an underlying, unsuspected structure, so long as you had the courage to leave gaps. And this sort of goes back to things like the periodic table, when Mendeleev was writing down all the chemical elements. If he realized if he arranged them according to function, then there were gaps, and that then predicted the existence of chemical elements. Well, we were predicting the existence of juggling tricks, and it worked. We actually found juggling tricks that no one had ever done before. And when we took these to juggling conventions, people literally sat at my feet for days to try to learn some of these tricks. And months later, at another juggling convention, people from, in particular, I remember going to the European Juggling Convention, and people from America were trying to teach me a juggling trick, which I'd shown people just a few months earlier at the British Juggling Convention. So these were tricks that had gone right round the world suddenly, and everybody thought they were new. Now, we don't know for certain that these had never been done before because there was no written record. But nevertheless, all the evidence is that these were entirely new juggling tricks, which now form a large part of the canon of early juggling. Some of these tricks are really easy, but some of them are phenomenally difficult. In fact, there's a 2-ball juggling trick that's pretty much as difficult as juggling 5. And there's a whole range of these. And of course, if you get this kind of thing happening, there's going to be some structure underneath. There's going to be mathematics to describe it. And so that's how we stumbled across unsuspected mathematical structure underlying juggling tricks. And then when I went to the British Maths Colloquium, there was a session that was going to be cancelled because there were insufficient speakers, and I offered to give a 20-minute talk. And I stood up and just sort of rambled on for 20 minutes about the maths of juggling with demonstrations. And afterwards, people invited me to speak at their son's local school and to come along to the local maths association meetings. And I did 3 or 4 talks that year, and that was in 1985. And since then, it's just continued to grow. And for the past 8 or 10 years or so, I've done between 80 and 100 talks every year, most of which are on the mathematics of juggling.
Colin also had this to add about the mathematics of juggling talk itself.
And people are there expecting a maths talk. And so I will spend the first half of the talk actually demonstrating the structure of the juggling itself, and then more or less follow the historical development, say how do we write this down? And I develop the notation, and I get to that point where I say, look, this can be done, this can be done, this can be done, what do you think comes next? And the audience predicts the existence of a juggling trick. And then I do it. And then the next thing I get them to do is predict the existence of a juggling ball that has to go backwards in time. And then I do that as well.
You can find out more about Colin Wright at his website, solipsis.co.uk. Our next story brings us to a cafe on the campus of Purdue University, and a simple question that I have long wanted to ask of a certain sociology professor.
You want me to do that now?
Yes, sorry.
I said you're going to do that.
Yes, I'm going to. Oh, so would you please do that?
Okay. Yes, my name's Scott Feld. I'm a professor of sociology here at Purdue University.
Okay, so my first question to you is, do your friends have more friends than you do?
I'm sure that my friends have more friends than I do, on average.
That may seem like an odd, even mean question to ask a person, but I'm going to ask you to trust that I have my reasons, which will become clear later on. Instead of dwelling on that, let's talk about Professor Feld. A sociologist might seem like an odd choice of interview subject for a show all about mathematics. But Scott Feld isn't your typical sociologist. Before he started going down the sociological path, he studied mathematics. In fact, that mathematical training has informed the way that he approaches sociological problems.
The task is to define sociological problems that are mathematically describable and solvable. I mean, if you can find the problems, the solutions usually follow. I think the problem with sociology as a field, why it's not more productive than it is because sociologists try to address impossible problems. I mean, and I think that there's probably an analogy in physics. As long as physicists were trying to turn lead into gold, they weren't going to make a lot of progress on that. And I think sociologists are busy trying to solve problems of racism and inequality and solve all the world's problems at one time. And those are they're important problems, but they're too big problems to be defined and managed and come up with any kind of solutions.
The work that brought Professor Feld to my attention came out of his collaboration with Bernie Groffman, a professor at the University of California, Irvine, on how people understand and experience the world. In particular, the way that people do not really understand the world. This led them to research the class size paradox.
The class size paradox was basically realizing that at, say, at universities or any place like that, there are class sizes, there are college classes that have 30 people, 100 people, 300 people, and that colleges would say the average class size was something like 30. But somehow other students were rarely in small classes, and they couldn't necessarily understand why. How could the average class size be 30 when all their classes were big? And so what we realized was that the reason is because for every 100-person class, there are 100 people in it, and for every 10-person class, there are only 10 people in it. And so if all classes were size 30, everybody would experience 30-person classes, but as soon as you have variation, a lot of people experience the big classes and practically nobody experiences the little classes. So the reality is that if the college has an average class size of 30, then the students experience an average class size of 80 or something like that, depending on the specific numbers. And that seemed to me an important insight that we published 40 years ago, I don't know, 35 years ago, that nobody's paid any attention to ever since.
While no one may have paid attention to the paper on the class size paradox, that didn't mean it was an uninteresting area of study. It just meant that Professor Feld would need to find a topic that would hit a lot closer to home with people than the average college class size.
I had thought about these ideas of class size paradoxes before and the bias in people's experience of certain types of situations. And because I spent a lot of time thinking about networks and talking about them, I just sort of came to realize in listening to some discussion that people would, if people were to compare themselves with their friends, or they would get these kinds of biased samples. And I sort of, my intuition said this would be true, okay? And because those friends have lots of friends and they would be disproportionately represented. And so I actually started to explain that to my friend and colleague, to Bernie, and it wasn't immediately clear why that should be the case to him, so that meant that I had to keep trying to figure out why it was true and try to explain, develop more precise description of what was going on and why. And so after I had the insight of what was going on, I then sat down and tried to actually develop the math for why and under what circumstances it turns out that way.
Well, people's friends and their relative numbers is certainly more central to most people's lives than class sizes. So it would seem that this paper should have a larger impact than the previous one. But more than that, it had a secret weapon. One that is very rarely brought out in the academic article wars. A fantastic name. After he had finished working up the mathematics and the paper was ready to be published, it was titled, "Why Your Friends Have More Friends Than You Do." I won't lie, this is easily my favorite academic article title, and is in my top 3 best titles ever. I mean, with a name like Why Your Friends Have More Friends Than You Do, how could it not be great?
I mean, in some sense, that paper should be 3 sentences long because the basic point can be made very, very quickly. The rest of the paper is actually just sort of trying to be precise about what it means for your friends to have more friends than you. Certainly all of your friends don't have more friends than you, so the idea is, well, do most of your friends have more friends than you, or is the average among your friends more than you, and is that true for everybody? And so once you start making the question precise, it gets a little bit more complicated, maybe a little less interesting, but you understand the kind of, I needed to spell it out. And so what I did is I just sort of worked through the details of how it worked, and I was delighted to discover that it really was the same phenomenon as the class size paradox, and so that the basic math was identical. I mean, that basically that the mean for the friends was the mean for the average person plus the variance over the mean. I mean, it's a very, very simple formula.
What he's talking about is now better known as the friendship paradox. Specifically, it's referring to the phenomenon that in a group of people, more than half of them will have fewer friends than the number of friends their friends have. As you can see, the term paradox is well deserved here, as that statement did not make much sense.
Basically, what it means is if you've got a set of people in a population or a group, and they all have different numbers of friends. So that some people have 100 friends and some people have 2. And friends are always symmetrical. So if you're my friend, I'm your friends. Then it must turn out that the people with 100 friends are the friends of 100 different people who get to count them among their friends. And the people with 2 friends are friends with only 2 different people who get to count them among their friends. And so if people took a representative sample of the friends out there, 100 of them would get a person with 100, and 2 of them would get a person with 2, and the average number of friends of the friends would be the weighted average of the number of friends of people in general. So people tend to get people with 100 friends 100 times compared with people with two friends 2 times, so they see those people an awful lot. And so you can calculate the average number of friends as the number of friends weighted by the number of friends. That's what it amounts to. Then taking a weighted average in that way is the way it works. So if there's a lot of variation, meaning that there are some people with a very large number of friends, then those people show up in everybody's set of friends, and they very disproportionately influence the way people see the world. If there's very little variation, if everybody's pretty much the same, then it doesn't make any difference, because then people see things appropriately if they don't really weight anybody any more than anybody else. Part of the reason it's important is because lots of studies and have shown that in terms of networks, in terms of anything like this, the variation is usually enormous. Okay, even the early studies of social networks and small groups in school classes and things like that showed that there are almost always one or a couple of people who were very popular, and then a lot of people who might have no friends at all, and as long as that's the pattern, then that has enormous implications for the way people experience the friends of their friends.
And while the title of the paper may seem harsh, Professor Feld had nothing but the best of intentions for the research.
But the friendship thing, I thought that would have implications. Actually, when I wrote the paper, I wrote it with a kind of emphasis on the fact that people because people's friends have more friends than they do, they get the impression that they are somehow socially inadequate relative to the rest of the world. And they are deficient, if you will, in numbers of friends compared to the people they're friends with, but those are a rather unrepresentative sample of people. Those are all those people with lots of friends. So I tried to say, you guys shouldn't feel so badly, because your friends may have more friends than you do, but those people are unusual, and that if you compared yourself to ordinary people, you'd probably find that you're just about the same as everybody else. And so I was kind of hoping to make people feel better by realizing that their feelings of inadequacy by comparing themselves to this biased sample were misplaced, and that they really ought to feel better. Everybody I've ever told that to responded by saying they feel worse. And so somehow or another, they didn't use that information in the way that I had hoped them, because all they did, what seemed to be the common pattern, was it focused their attention on the fact that their friends had more friends than they, which they ordinarily didn't pay that much attention to. So that made them feel worse. And telling them that was misleading because average people aren't like that didn't impress them any, because their friends were like that.
Do you know what else can make people feel poorly? A contagion. Trust me, this segue works.
Well, a contagion, I mean, we borrow metaphors and ideas, of course, from biological contagion, where one speaks of the contagion of a germ, but of course one can speak about the contagion of ideas or behaviors, and here we mean just a person-to-person-to-person spread of some phenomenon.
That was Nicholas Christakis, a physician and social scientist who works as a professor at Harvard University in the departments of healthcare policy, medicine, and sociology. So he is rather qualified to speak about contagions, whether biological or not. In fact, Dr. Christakis, along with his collaborator James Fowler, conduct research into the relationships between people's social networks and their health. The thing is, in order to do such research, you need those networks.
So this is always the problem. Whenever you're trying to discern a network, you need not only the collection of the constituent elements, the nodes in the network, like the people in our case, but you also need information about the ties between people. Either you need to collect this from scratch, for instance, by talking to all the people that are part of the population and asking them who they're connected to. Or nowadays you can, of course, use administrative and electronic data, what we call massive passive data. Phone companies, online social networks, blogs, other kinds of data that exist that allow you to discern who's connected to whom. One way or another, though, either by collecting the data from scratch or taking advantage of pre-existing data, communications data, and so forth, you need to discern who's connected to whom.
So what can a researcher do if that data isn't available?
If you can neither talk to anybody to discern the ties nor take advantage of existing data, you can do some other tricks that give you network information without mapping the whole network, like this friendship paradox trick that we deployed.
See, I told you that segue made sense.
Now, the reason this so-called friendship paradox is extremely valuable and that we used in some of our work is that you can pick a random sample of people, have them nominate their friends, and those friends will have more friends than they do, will have higher degree, and be more central on average in the network. And you can find those people without mapping the network. And now once you've found those people, you can either talk to them or you can passively follow them as we did, and you can treat them, for instance, as a kind of sensor. So in one project we did is we reasoned that the central people should be more likely to get whatever's flowing through the network and more likely to get it sooner in the course of an epidemic. So if we could find these central people and monitor them, we could get an early warning system for what is flowing through the network. Not just predict what's going to happen, not just monitor what's happened in the past about the epidemic, but predict what's going to happen in the future of an epidemic. Because if we see the epidemic spiking in the central people, we know soon it's going to hit the population at large. And so we proved that, James Fowler and I, working with a flu outbreak, an H1N1 flu outbreak at Harvard College a year or so ago. We took a random sample of students, we had them nominate their friends, we followed the epidemic both in the random group and in the friend group, and sure enough it spiked and peaked in the friend group sooner, by one metric, 6 weeks in advance of peaking in the random group. So we were able to tell that the epidemic was about to strike the population well over a month before anyone else knew. And actually this idea can work not just with germs, but with the spread of ideas, with the spread of information and behaviors, and anything that spreads in the network. You can use this trick to forecast the future.
Did you get that? The friendship paradox can help you forecast the future. All joking aside, a 6-week early warning on an epidemic is a great result, and this research could well result in advances that might just help save people's lives. I made sure to ask Professor Feld what he thought about this work.
So, what was your reaction when you then heard about the work that Nicholas Christakis was doing with your friendship paradox?
I really like that idea because it makes perfect sense, but I for one, think that things that make, if science and social science could often find things that are obvious once said, I'd be very happy, because a lot of things are obvious once you say them, but nobody either thought of it or paid any attention to it before. And I'd be perfectly happy if I myself could just sort of discover things that are obvious once I say them. I mean, at least for a while, I think there's a lot of room for what sort of low-hanging fruit in that regard. And I think that what they did is one of those kinds of things, which makes why didn't everybody think of that before? Because it seems like an obvious kind of thing to do. But of course, it is more complicated when you actually get into it. But I think it's a great idea.
Actually, the professor thinks that they may have stumbled on something even better than they realized.
What they wrote in their paper was that in order to, what they wanted for advanced sensors was people who were centrally located, who were very well connected. And what they said originally is that if they had the whole network mapped out, they could locate the central people and use them as advanced sensors. And they said that they only resorted to using the friends of a random sample as a second best approximation to what they would have preferred to do if they had all the network information. But I think that that's actually not quite right, because the central people, essential people in a network might themselves be a set of very closely interconnected people who are, if you picture a network as having a center and a periphery, and you take only the central people, you're going to get the people literally in the center. And at least I imagine that you could have a lot of spread of disease in the periphery. It couldn't spread to the whole network easily, just from the periphery to the periphery. But you can get a lot of things going on out in the outskirts without the center getting involved. And if you only paid attention to the few people in the center, you might miss something important going on. On the other hand, I thought that it was brilliant that they took this friends of a random sample, because that kind of addresses that problem. Because by using a random sample, you're going to represent the periphery as well as the center. But you're also, by using the friends of a random sample, you're getting people that are better connected than a random person. So you are representing the whole network intentionally and deliberately, so you're not going to miss isolated pockets of disease, okay? But you're getting a better representation than a random sample because of better representation in the sense of representing where the disease happens, because the people with more ties are more likely to be where the disease happens, and you want to overrepresent those as in order to find how much disease is out there.
Starting with the sizes of college classes and ending with predicting epidemics is not too shabby for an idea that was just trying to explain how people experience the world. And who knows if it's done yet.
The basic point is that, the basic point of the Friends paradox and of class size paradox is that people experience the world selectively. And that selection has to do with certain patterns of experience, like people experience things in groups. So people experience things in classes, people experience things in various bunches. They don't experiences are not random, individual, isolated experiences. And that has a very broad set of implications for the patterns of experience and the overall experience of a society at large and of the way people perceive that society. That has broad implications, only some of which we've sort of tapped into a little bit. But it's hard to anticipate. I guess maybe like all networks, you see the next step, but the step after that may not be visible yet until you take that step fully and you get closer to and then you can look to the next step from there.
Our final story is about the king of the mathematical constants, pi. Pi, or to give it a more precise definition, the constant derived by dividing a circle's circumference by its diameter, has been around for thousands of years and has played a very important role in the development of mathematics. So much so that it almost seems to be a sacred object. That's why it was such a surprise when I stumbled upon an article written by Professor Bob Pillay, then at the University of Utah and currently at Utah Valley University, entitled Pi is Wrong. This was so unexpected, in fact, that I had to get him on the phone so he could explain himself. Is pi not 3.14 and so on?
Oh, pi absolutely is 3.14 and so on. The problem is that that's not the right number that would be the most useful and natural. The most common use of pi is the reference to angles in terms of full turns of a circle. People have trouble with trigonometry because they measure a right angle, which in our reference pi 3.14, to pi over 2. And if you ask the average, even scientifically informed person on the street what's 90 degrees in radians, they'll say, oh, I don't remember. But if you ask anyone what 15 minutes is, they'll say it's a quarter of an hour. So there's the discrepancy. Pi over 2 for a quarter of an hour. It is a kind of a disconnect and a cognitive dissonance that I think makes one of the most beautiful areas of mathematics, trigonometry, and all the circular functions seem a little bit less natural. And because of that, I think we lose a lot of people very early in math because we try and tell them this is the most beautiful thing in the world, and it's got a little bit of a kind of a problem with it. And there's so many articles that talk about how perfect and eternally beautiful pi is and all this wonderful stuff, and I just couldn't resist having a little contrary point of view that pi is wrong. Really, my entire motivation is to make things more understandable for students and colleagues when I'll do any more standard math. Conveying the main ideas is important. And I think pi, the pi 3.14, detracts from conveying ideas.
So what kind of brought on the insight to you that this constant that we've been using, that we've been teaching to people for so long, and literally thousands of years at this point, that it wasn't actually the one that we should be using?
Well, to me, I know the exact moment that I noticed it. It was while giving a test in class, in a calculus class. But I do have to say that although most people have stuck with pi for hundreds of years and more, several people have thought of this before. Someone found in Fred Hoyle's astronomy book, very classic astronomy book, he talks about measuring things in turns, which were our full revolution. But the moment it occurred was in the class because I wanted to make my exams be easy to answer without a calculator. So I had the answer turn out to be sine of pi over 2, even though the answer was sine of pi over 2, which is 1, which people should know from circle diagrams. I would see all my students going to their calculators and plugging in pi over 2 sine. I'm saying, why can't they see that sine of pi over 2, that pi over 2 is this making a right angle with my fingers, my thumb out to the right and my pointer straight up? And I looked at that and said, why don't you see that this is pi over 2? And I kept looking at it and I said, wait a minute, that's not half, that's a quarter. It's a quarter of an hour. It's the exact symbol you'd make if you were trying to show someone 3 o'clock or something, or 15 minutes, a quarter of an hour. So now when we talk about 270 degrees, 3/4 of a turn, what do we call it next with our old pi? 3 pi over 2. So you'd say, I'm going to be there in 3/2 of half an hour. The more I look into things, the more I see places where 6.28 works out much more nicely as the right number. If we just got rid of symbols and just put in numbers, circumference is 6.28 r, and so forth, we'd see that was the number that came up more often and more naturally. We like pi. I think we're all very fond of pi. Pi is great. It just wasn't the right number for simplicity and beauty and to show the real essence of the beauty of circles. I don't think I'm the world expert on pi necessarily, but I just made a pedagogical observation that maybe a reason that our students have trouble is that measuring angles in terms of half turns is really unnatural and unmathematical. There's a possible solution by giving a symbol to 6.28. I had an idea of having a circle icon with a radius rather than a diameter. My father suggested 2 pi's joined together at the middle, so a 3-legged pi. Most recently, various people have proposed using tau for 2 pi, for 6.28, for the circle constant, and referring everything to the symbol tau. And that actually has caught on much more thanks to Michael Hartle's Tau Manifesto.
My name is Michael Hartle, and I am the founder of Tau Day and the author of the Tau Manifesto.
So I was wondering, Michael, why or how you kind of first came to realize and to understand that pi is useless.
Well, I wouldn't quite go so far as saying pi is useless, but it's certainly confusing. And I think I suspected this for a long time, but what really crystallized it was reading the paper that I mentioned in the Tau Manifesto called Pi is Wrong by Robert Pillay, who's a mathematician at the University of Utah. So I read that paper shortly after it came out in 2001, and it was clear to me at that point that his argument was basically right. What's wrong with pi is that circles are fundamentally about their radii and not their diameters. So the number that characterizes a circle is its radius. So a circle is the set of all points a given distance, the radius, from the center. Diameters are not a particularly important geometric idea with respect to circles. If you write things in polar coordinates, for example, or if you want to come up with a succinct definition of a circle, it's extremely cumbersome, sometimes impossible to use the diameter instead of the radius. So that suggests that C over D, which is just C over 2R, might have a factor of 2 difference from the more convenient notation, which is C over R. So tau is my proposed notation for the number C over R. And if you do a little math, you can see that C over R is just 2C over 2R, which is 2C over D, which is 2 pi. So numerically, tau is 6.283185, etc. Probably the most severe problem in the elementary curriculum is the case of radian angle measure, because the idea of radians, which involves comparing the arc length of a circle to the radius of a circle in order to define angle, leads naturally to the notion of a full turn. That is to say, the radian angle measure of a full circle. And that number is 2 pi when written in the traditional notation. The problem with that is that if you start to define the angle measure for certain fractions of a circle, say an eighth of a circle, that has radian angle measure 2 pi over 8, but the 2 cancels because there's an even number in the denominator, and you end up with pi over 4. So an eighth of a turn is a fourth of a pi. A quarter of a turn, which is a right angle, is a half a pi, and so on. But if you write these angles in terms of tau, there's nothing to memorize. An eighth of a turn is just tau over 8. A quarter of a turn is tau over 4. A half a turn is tau over 2, and a full turn is just tau. So there's nothing to remember. You can just say, well, I know a right angle is a quarter of a full turn, and so it must be tau over 4 radians.
Now, there's all these examples in mathematics of what people consider to be beautiful equations where pi is a part of them. So what would changing to tau instead of pi do to something like, say, Euler's formula?
Well, the Euler's formula itself is actually e to the I theta equals cosine theta plus I sine theta. And the special case of theta equals pi is usually called Euler's identity, and that says that e to the I pi equals -1, which is usually rearranged right away to form e to the I pi plus 1 equals 0. Put in tau instead, there you see that you get e to the I tau equals 1. I mean, to me, that looks nicer. Like, what is e to the I pi equal -1? There's a negative sign. It requires being rearranged. The real way to appreciate that is to realize that complex exponentiation corresponds to rotations in the complex plane. If you multiply a complex number z by e to the I theta, it's the same as just rotating that number in the complex plane by an angle theta. So you can see that e to the I tau equals 1 is telling you that the complex exponential of the circle constant of 1 turn is equal to 1. If you rotate by 1 turn, you just get back to where you were. It's the same as multiplying by the multiplicative identity. E to the I pi equals -1 is telling you that multiplying by half a turn is the same as multiplying by -1.
That's all fine and good, but what about something like the area of a circle, which is nice and clean as it is? Wouldn't we be introducing fractional numbers if we replace pi with tau in that case?
It looks that way if at first glance, but if you look at the way that the area of a circle is actually derived, it involves a factor of half. Look at the original proof by Archimedes, which showed that the area of a circle is equal to the area of a right triangle with base equal to the circumference and height equal to the radius. So the area of a triangle like that is 1/2 base times height, which is 1/2 circumference times radius, and circumference is equal to tau r, so that you get, in that case, 1/2 tau r squared. If you use calculus, you see it in a different way. You can break up a disk into circular rings and integrate over all the rings, and what you get in that case is the integral from 0 up to the final radius of tau r dr, which is equal to 1/2 tau r squared. No matter how you approach it, there's a factor of 1/2 that comes from naturally from the derivation. Using pi r squared obscures that relationship, and indeed, if you look at the derivations in those cases, you have c equals 2 pi r. There's that factor of 2, and it cancels against the 1/2. So what's really going on is it looks like it's pi r squared, but it's really 1/2 2 pi r squared, and it's the 2 pi that's fundamental.
I was wondering, what brought you to writing the Tau Manifesto in the first place?
There are a whole bunch of different reasons. Probably the most important is that it was just a tremendous amount of fun. I saw an opportunity to make something that I thought was really cool, and that I thought other people would also think is cool. What happened is that Bob Paulet's article got quite a lot of attention on various social news sites like Reddit and Hacker News, and I could see that there was an opportunity that was in the air. People knew about this, but it hadn't become a movement. And one of the things I'm interested in is learning how to build an audience and how to really connect with an audience. I saw that there was this thing out there, and I thought I knew why it hadn't taken off. I thought a big part of the problem was that the notation wasn't quite right, that the notation that Bob proposed was very difficult to typeset. I also thought that it would be good to have a focus for this idea. So that's how I came up with Tau Day, this idea that instead of Pi Day, we should be celebrating Tau Day instead. So it really was an experiment in making something cool and seeing if I could find an audience.
What sort of reaction have you had to this whole thing?
Well, the reaction from the mathematical community has been more or less muted, but the general reaction from the broader sort of mathematically interested public has been overwhelming. The Tau Manifesto website on any given holiday like Tau Day or Pi Day gets, tens of thousands of visits. It's got over 3,000 likes on Facebook. I get email about it all the time. The MIT admissions office made a blog post before, in advance of their admissions decisions in March, with like little illustrations of the two warring tribes, the Pi tribe and the Tau tribe. Traditionally, MIT has released their admissions decisions on Pi Day. This year, they released them on Pi Day at Tau time. So it's at 6:28 on 3/14. Gotten to the point where in any decently sized room of math or computer or science geeks, the chances are really high that somebody there knows about the Tau Manifesto.
A lot of this has to do with pi not really being a very useful constant in many ways. So how do you see that, or how would you suggest maybe making that switch? How can we go from a constant that's probably not defined in the right way to a constant that is?
I'm not proposing a change in any sort of convention. It's not like we're switching from charge carriers being positive to charge carriers being negative. This is an extra piece of notation. It's an addition to the set of mathematical constants. And so as a result, any change you make can happen incrementally. Start by using tau in your own calculation. If you want to write a paper, you can just say we work in terms of tau equals c over r equals 2 pi and proceed from there. In fact, I got an email a couple months ago from a master's degree student in Europe who got permission from his committee to use tau in his mathematics master's thesis. So there are people using it, and I think that as time goes on, more and more people will take that approach. They'll just say, you know what, I'm just going to use tau in my calculations.
Well, this has been really good. Thank you very much.
You're very welcome.
I just have one last thing to ask you here. For such a long time, people have viewed pi as being, as you said, just this beautiful, amazing little bit of mathematics. And also, since it's the circle constant, and the circle is a very natural sort of shape, we've long thought that every different alien civilization in the entire universe would probably also have the digits of pi. And so one of the ways of contacting these aliens has been to send out the digits of pi. What would your opinion be of the probable reaction of an alien race if they intercepted 3.14 and so on and so forth?
I think there'd be raucous laughter and then a big discussion of whether they should maybe avoid this planet, because the people there obviously are very dogmatic and not open to thinking about new things. So we brag to the universe about our intelligence by sending out, they were thinking about, why are they sending out half the circle constant? Well, a friend of mine pointed out that if we are lucky enough, we sent it out in binary, and then we just got the binary point off by 1. So maybe we got lucky and they're thinking it was just a typo, and they really know where things are at.
Oh, Professor Pillay, it's been an honor speaking with you. It's been a lot of fun.
It's been a lot of fun. It's been an honor speaking with you, and best of luck with your project.
I'm Jen Bokoff of jenbokoff.com, and I'm one of the Relatively Prime funders, and that is it for Relatively Prime this time. We want to thank the guests: Sir Timothy Gowers of Cambridge University, Colin Wright of solipsis.co.uk, Scott Feld of Purdue University, Nicholas Christakis of Harvard, Robert Pillay of Utah Valley University, and Michael Hartle of towday.org, and the musicians HJL Phillip, Ronan Beats, Red Shirt Beats, and Mashmall. Without all of you, this would not have been possible. If you want to find out more about the guests or the music, or if you want to discuss the show, please join us over at relprime.com. That's REL Prime.com. Oh, and while you're on the internet, why not head over to iTunes and leave a review of the show? It really does help other people find the show. And if you have any feedback about the show, just email Sam at samuel@acmescience.com. It's his personal email address. Spam him a lot. Relatively Prime is licensed under Creative Commons Attribution Share-alike license, and any remixes are greatly looked forward to. Thank you for listening, and we hope you come back for the next episode.